Okay, hello Nidir. Let's get started. I just thought I'll make a video anyway on magnetic fields. This seems like a very easy chapter actually. I was going through it. Just one formula, one concept, one idea. So we'll just talk through it. Actually two ideas mainly, and just one formula. So we'll just talk about it. It is a very easy chapter. And we'll just talk about things around it, right? Okay. So pretty straightforward thing. So we are starting with a new topic called magnetism, right? So till now, what we had seen, if you remember, we had seen like uniform electric fields, Coulomb's law, and capacitance. So all of that was about charges, right? So we had a plus charge, and we were talking about what the effect is on another at this point, right? And what is the force that it experiences here, or what is the field that it has here? So we found that E field here was given by uh, 1 by 4 pi epsilon naught, right, into q, if this is the q, by r square if this is the r, right? So now if you place another charge here, um, which is say a capital Q right there, so then the force on this charge would be given by the capital Q times this electric field. So electric field was said to be force per unit charge, like so force on one unit charge. So if there is more than one unit charge, like Q units of charge, so the force will be Q times uh, the the electric field. So that, so net it becomes 1 by 4 pi epsilon naught and q by r square, right? So this is what we saw was the electric force, or the force due to the electrostatic, or the due to the charges. Is that right? We discussed all of this. So this is what we called Coulomb's law, right? So Coulomb's law was due to charges uh, attracting or repelling each other. Okay. So that is what we have done seen till now, right? So now we are shifting a little bit. Now we are talking about magnetic fields, right? So the idea behind magnetic fields is we first, which is this first key idea. The idea is not stationary charges but moving charges, right? So in Coulomb's law, we only talked about charges. Either they are moving or stationary, they will still have an effect. But here we are only talking about moving charges, and moving charges is what we call current, right? So if we have a current in a wire, right, it does something interesting. Only if it is moving. Okay, if it is a electron that's kept anywhere, that's not important. If the charges are moving, then what we see is, if we keep iron fillings around on this surface, right, they tend to organize them into a circle, right? Or an easier example would be if you bring a compass here, right, you see that that compass deflects, right? And because we know that compass responds to magnetic fields, so that means there is a magnetic field. So what we are seeing is that moving charges are producing a magnetic or a B field. We use the word B for magnetism. So instead of an, so all charges which we see produce an E field, which is the electric field that we saw previously in the last slide. All charges, whether stationary or moving, but moving charges produce a B field, right? So a moving charge will produce both an E field and a B field in a way. Okay. So, okay, so then we want to say certain things like how does this field look like? So, first thing is it looks like circles, right? So that is different from how it looks like from positive charge, which is the E field. E field looks like it goes out in spokes, right? And if there's a minus charge here, then it goes back down into this, right? Like it goes inside the negative charge. That's what we have seen. But in opposition to this, uh, let me draw it on the next one. So in opposition to this, if we have say X like this. So X means that the current carrying conductor is going into the paper. So imagine it as an arrow, right? Our arrow analogy. So there is a cross sign at the back, right? And if this arrow is going into the paper, then all you will see is a cross sign at the back. right? So this is going, so this is a current carrying wire that whose current is going into the paper, right? In that case, it produces, uh, so imagine like our setup is like this. So this is current that's going into the paper, right? So we are talking about the point here and the B field on the sheet of the paper, on the plane of the paper. So we say that if the current carrying conductor is going into the paper, then we use the right hand rule, and we say that the magnetic field lines will be, you point your finger in the direction of the thumb, so that's into the paper for me, and then you wrap the hands around, right? So the question is whether it will be clockwise or anti-clockwise, and we see that my hand wraps around the clock, right? So it is clockwise, right? So that's your motion, that's the direction of B field, right? So that is your first key idea, that moving charges or current produces a magnetic field, and the magnetic field direction is given by what we call the right hand rule, right? So similarly, uh, if we have so right hand rule is also used in this way, that if you have a, so you can do a few exercises, like try to see what happens to this, like, so this is a wire who is coming out of the plane of paper, so it will be the same thing but opposite. So you can just check it, so you can point a thumb up and then you will see that it goes anti-clockwise, right? If it is sideways or something like that, then also you will see. Okay, so what about, let me try to trick you a little bit. What if the wire itself goes like this? So the current is going like this. I'm now, this is the current, okay? And I'm asking you how the magnetic field is. Now, because the current is changing direction, everywhere it is different, right? So let's talk about this segment maybe first. So this segment, so you point a direction along the sheet of the paper, and it rises from the one side and goes back into the other, right? So the magnetic field here is coming out. So coming out is a dot here and is going in here, right, with respect to this one. Let's check the second case, this guy. So again, it is, we put our hand along the current and then try to draw the magnetic field. So magnetic field now is coming. These dots represent magnetic field. So it's coming out and then wrapping around into the plane of the paper. So inside it's coming inside, right? So similarly, if we try to do for this guy, so it's coming up now. So now we wrap the hand around this time, comes up from this side and goes into this side. And finally on the upward side, so it comes out from this side and goes into this side. So on the whole, if you have a current carrying loop, right, so all of the magnetic field lines in a way look something like this, right? Like all of them go into the loop on the top and come out of the loop on the bottom. So in this middle area, the highlighted area, let me just make it a different color as well. It's not a good color. So this area is this area right here, right? So here it is, all of the wires are going into the plane of the paper, and on the outer thing, they're all coming out, right? So what I mean by that is, it's coming out of here, it's going up here, and it's going up here, right? Like it's shooting up. Is that fine? Like this is just an exercise for you, but it will be important like two or three chapters down the line. Okay, so that's the first key idea, that current carrying conductors, moving charges, produce a B field. Okay, okay. So that's fine. So that's good. Now this is a different idea. Now we are saying, this is the second key idea. We are saying if a current carrying conductor I, right, is already there in a B field, already present in an external B field, right? So the idea is someone else is producing a field, say the field is pointing along the sheet of the paper, and you have a current carrying conductor inside this. Okay, so the current is flowing like this, right? Again, you need moving charges for this. All of magnetism is about moving charges. Okay, no stationary charges. So you won't talk about an electron, but you will talk about a current, right? So now you have a B field of strength B, right? Or whatever B is, and you have a current carrying conductor that's carrying the current I. In that case, this current carrying conductor jumps, right? It experiences a force. So that's the main concept here, right? So earlier what we said is if there is an isolated current carrying conductor, nothing else, then it itself will produce a B field. Now we are saying that like that current conductor is in an external magnetic field, like say the Earth's magnetic field. Then in that case, this thing, so you can say that this will produce its own B field here, right, in circles, and this B field interacts with the other B field to produce a net force, right? So ultimately there is a force, and that force's direction. So force is there. So force's magnitude is given by IBL, where I is the current in that conductor, B is this thing, and L is the length of the conductor in the field. So it is only from this point to this point here because there is no field externally, right? If this field were to extend, then yes, UL would be larger. So this is the net force. And what is the direction of that force? So direction of the force is given by uh, Fleming's, the spelling is wrong, left hand rule, right? So the idea behind the left hand rule is simple. You can refer to textbook also for this. So your middle finger, let's do it in the next one. So middle finger, you have to point it like this. Middle finger represents the current, right? Your pointy finger, your index finger represents the B field, and your thumb then represents the direction of the force. So ultimately you are trying to find the direction of the force, right? So let's try to do this example that we're trying to do. So B field is like this and I is like this. So let's point our thumb in the direction of the, point our index in the direction of the B field, and let's point our middle finger in the direction of the current, right? So this is going right, this is going upwards. And so my thumb, as you can see, is pointing into the plane of the paper, right? So my force direction is into the plane of the paper, right? So that is the thing here. That's the key idea. Okay, so let's do another question. Say maybe now your B field is, let's do a question from the book actually. Um, yeah, so B is also called the magnetic flux density, by the way. So F is yeah, this B is called the magnetic flux density. That's fine. Yeah. So maybe let's try to look at this question. Yeah, like I highly recommend that you look at the questions here because I'm trying to cover things a little bit faster for the sake of time. So let's see what is happening here. It's saying that there's an arrangement shown in this figure. The balance reading changes from this to this when the current is switched on. Right? So what is happening here is there is a north pole on this side, on a south pole on the other side. Right? And the magnetic field lines will go from the north to the south. Right? And then there is a current carrying conductor that goes through it. I. Right? So they have not given the direction here. So they are saying that the reading on the scale, it changes because of this. So it has some natural weight that it wants to have, but after you switch on the current, the reading changes. So the question is, like, can you justify what is the direction of the current and the size of the force on the wire, right? Uh, so because the weight is changing from 102 to 104, that means the weight is increasing. That means there must be an additional force that is induced uh, by the magnetic force on the wire, sort of a thing, right? And that force is given by IBL, right? In this, what? Yeah, right. So it's IBL, uh, here we can't find that exact number because B and all are not given, but what we can certainly say for sure is the force must point downwards, because it at the end of the day increases that scale reading, right? For you to have a downward force on this wire, so we need to apply the Fleming's left hand rule, but in reverse. So we already know that the thumb points downwards, right? And the B field must point from north to south, right? And if it does that, then we can see that the current direction is going from this side to this side. So you can do some visualization and try to do this. And it can be a little bit tricky, but yeah, once you get used to it, it will be easier. Okay. So those are the two chief ideas. Let's talk about the ideas surrounding it. So one thing that can happen. Uh, okay, one more thing to look at is maybe this diagram for more practice. So if there is a B field and you're wrapping the current conductor around like this, right? So you only experience a force when you cut through the magnetic field. So what I mean by that is, what the example that we saw was an B field like this and a current carrying conductor that is straight upwards, right? So it is cutting through the field. So it experiences a force as we told. But if you have a current carrying conductor that's like this, so along the B field, then it experiences no force. So force on this red wire is 0, but force on the blue wire is equal to what we told is IBL, right? So naturally a question arises that if say it is at an inclination or angle theta, right, to the B field, then what is the force on the yellow wire, right? So it is IBL into this sine theta factor that we put. So if theta is 0, then this force becomes this scenario, and if theta is 90, then this just becomes 1, and then that is this guy. Right, so the complete formula becomes basically IBL into sine theta, where theta is the angle between the B field and the I, right? So I is here and B field is going flat, right? Okay, so in consideration for that, so if it is cutting through, that means it is 90 degrees. That means you will experience a force, right? So imagine this scenario which is shown here. There's a current carrying wire that goes here, comes wraps around, and then comes back out, right? So you can see at this point in this segment, it is going along the magnetic field line, so there will be no force here. But on these lines, it is cutting through the magnetic field in opposite directions, right? And now we apply the Fleming's left hand rule, right? And you will find that the force is downwards here and the force is upwards here. So net it tries to move, it tries to rotate, right? If there is something that is upward pressure or lower pressure, and then it will try to turn slowly. Okay, so just try to take some time to understand this. Hopefully you will, it is not very tough to follow. Try to work through this worked example, so it will help. Okay, yeah. Okay, another idea is to say that we have, so now we try to link those ideas, right? So the first idea was that if you have a current carrying wire, then that produces a B field, right? What we saw according to the right hand rule. So there's a wire, and that the thing that wraps around is the direction of the B field. The second thing is what we say is if there's a B field and there's a current carrying wire, right? That experiences a force. So so one of the things that we can try to combine these two ideas, and we can say what if this B field was produced by another current carrying wire, right? So there are two current carrying wires. So this one uh, and say another current carrying wire, say with a different I2 here. So this first I1 say produces its own magnetic field, right? Which is in circles, and at this point, this magnetic field interacts with this current to produce a net uh, force. right? So it might be like a little bit out of the plane of the paper on this B field, right? So because this would have experienced a force if it was in an external B field, but instead of being an external B field, that B field is being produced by this side. And what we see is this follows the like Newton's third law as well. So if this experiences, if there are two current carrying wire, one experiences a force like this, so other one, the whole thing can be applied in reverse. That this can be seen as the source of the B field. So this will experience a force in opposite direction. So it is consistent with Newton's third law as well. There are no formula there, but the idea is to just kind of elaborate on these things. Okay. Uh, okay. So once you do the question like a little bit, you will realize that the units of the B field are called Tesla, and one Tesla is usually very high B field. Uh, what we observe is Earth's magnetic is around 1 Gauss, which is about 10 power minus 4 Tesla. Like it is like this is the usual like unit that we use. So we at least scale it by an order of like 10 power minus 4. So these are the two common units for magnetic field, right? Okay. Okay, and the last idea that I want to talk about here is this comparison between. So at this point, we have seen three different kinds of fields. We have seen the gravitational field, we have seen the electric field, and we have seen the magnetic field. So these are all represented by electric field E, magnetic field B, and this is represented by little g, right? Which was acceleration due to gravity also, but it is represented by F by m. This is represented by F coulomb by Q, and this is represented by F force, which was calculated by the current carrying conductor by I into L, right, in a way. So all of them are defined in a similar way. So common characteristics are that they act at a distance. So the idea is they are what we call non-contact forces. Like they can be far apart, one current carrying conductor and we see a force, right? You don't have to push it or pull it, but it just happens at a distance, right? So one electron kept here, one electron kept here can attract each other. One mass here, one mass here attracts each other. Another current carrying wire will both have attractive forces, right? So just stuff like that. So that's the first key idea. Second key idea is they get weaker with distance. Like so, if you increase this distance, right? So these forces, if you remember, gravitation has a proportionality of 1 by r square, right? Gm1 m2 by r square. This has also 1 by r square, like 1 by 4 pi epsilon naught r1 r2 by r square, right? So all of these kind of drop off as you increase the distance. Okay. Um, and the last thing that we see here is the relative magnitude, just comparing them. So if you have 1 kg 1 meter apart, right, or 1 coulomb 1 meter apart, or say 1 ampere of current 1 meter apart, then relatively it is seen that the highest one is the electric force between them. So electric force is 10 power minus 9, so it is very strong, but gravitational force is very weak, it is 10 power minus 11, and magnetic force is 10 power minus 7, so that's somewhere in the middle, right? So if you were to keep like say one wire 1 kg and 1 coulomb here and try to measure the force, you would have to first, like, you would feel the strongest because of the charge, then because of the current carrying wires, and then because of the shear presence, right, the mass attraction of them. Okay. Try to do all the questions here inside the chapter at least, and that should be enough, I think, for this one. Hopefully, like, the main idea is to learn to apply the Fleming's left hand rule and just try to learn that one formula, that IBL sine theta, that's there, right? So like things like this, where field line is at an angle, you should be able to do these kinds of questions. Okay, sounds good.